Hello guys, in this video we are going to discuss the solution of the problem shortest path in undirected graph. So let us look at the problem statement. The problem statement says you are given an undirected graph having unit weight of the edges. Find the shortest path from source to all the vertex, and if it is unreachable to reach any vertex, then return -1 for that vertex. So for instance, if this is the graph which is given to us and the source is 0, then we need to compute the shortest distance between 0 to all other nodes, and that is what we are going to return over here. And in the second example, as you can see, the source is 3, the graph is this. Since there isn't exist any path from 3 to vertex 2, because of which this field is set to -1 and rest other fields are populated appropriately. So that's about the problem statement, folks. Now let us discuss the solution of this problem. So let us say this is the graph which is given to us and the source is 0. The first thing which we are going to do is we are going to represent this graph in adjacency list format. So this is the adjacency list representation of the graph. Now what we are going to do is we are going to take two lists. One is the visited list, and the length of this visited list is equals to the number of vertices, and initially all the entries of visited list is set to false, indicating that none of the vertices are visited yet. Similarly, we are going to take an answer list, and initially all the values of this answer list is set to -1, which indicates that as of now the vertex is not reachable from source. So once we have these information with us, which is answer, visited, and graph, what we are going to do is we are going to perform BFS. And while performing BFS, we are going to populate visited and answer list in order to compute the shortest path from source to all vertex. So let us see how we will be able to do that. So as in BFS, the first thing which we are going to do is we are going to take a queue, and within that queue the source will be pushed. So the source is 0, and corresponding to source we are also going to put a weight which is 0, which simply means the distance between source to source is 0. Now once we have this information with us, we are going to mark 0th node as visited. So this 0th node is visited, so we are going to mark it as true. And then we are going to check our adjacency list in order to see what are the neighboring vertex from source. So as we can see our adjacency list, from source the neighboring vertex are 1 and 3, which we can see it from the graph itself. So now we are going to iterate on this vertex 1 and 3, and we are going to check whether vertex 1 and 3 are already visited. Now since vertex 1 and 3 are not visited, because of which we are going to mark an entry or push 1 and 3 node on the queue. So let us push 1 and let us push 3. And the distance to reach 1 and 3 will be just 1 unit, which is 0 plus 1. So this will be 1. And since we have operated on 0, because of which we are going to pop this element from our queue. And once we pop the element from the queue, the weight is something which we are going to mark it over here. So the weight is 0 over here, which is for vertex 0, because of which this we have marked it as 0. So the next thing which we are going to do is we are going to take the next element from the queue, which is this element, and again we are going to check our adjacency list in order to see what are its neighboring elements. So as we can see, from 1 the neighboring elements are 0 and 2. Now as we can see, 0 is already visited, because of which 0 will not be pushed again onto our queue. The next neighbor is 2, and that is what we are going to push it onto our queue. So let us push 2 onto our queue. So 2, and what is the weight? Well, the weight will be equals to the current weight plus 1 unit. So this will be equals to 2. And since we have operated on this node as well, so we are going to pop this node from our queue, and we are going to make the appropriate entries in the answer and visited. So answer corresponding to node 1, it will be 1, the weight is 1, or rather the distance is 1. And similarly, since node 1 is visited, because of which we are going to mark it as true. Now the next element in our queue is this element, which is 3, 1. Again, let us check our adjacency list in order to see what is the neighboring vertex of vertex 3. So as we can see, the neighboring vertex are 0 and 4. Since 0 is already visited, because of which we are not going to push it onto our queue, we are going to push just 4, and the distance for 4 will be the current distance, which is 1 plus 1. So this 2. And since we have operated on this node, so we are going to pop it from our queue and we are going to update our answer and vertex. So 3 has been visited and the weight for 3 is 1 unit. Now again, the next element is 2, 2, and from 2 we can go to 1, 6. So let us analyze for vertex 1, 6. Since vertex 1 is already visited, so as we can see, vertex 1 is already visited, because of which we are not going to push 1 onto our queue. But vertex 6 is not visited, so we are going to push vertex 6 on our queue and the weight will be 3. And since we have operated on 2, 2, so we are going to pop it out, and corresponding to true, we are going to mark it as true. And for 2, the distance is 2 unit. Next element is 4, 2. So for vertex 4, the neighbors are 3 and 5. Since 3 is already visited, because of which we are not going to push it onto our queue. And since 5 is not visited, we are going to push 5 into our queue. And since we have operated on this node, so let us pop this from our queue and update our visited and answer list. So since 4 is already visited, we are going to mark it as true. And the shortest distance between 0 to 4 is 2 unit. That is what we are going to update it over here. Now the next element is 6, 3. And from 6, the vertices which we can visit is 2, 5, 7 and 8. So let us operate on these vertices. So as we can see, 2 is already visited, so we are not going to push it onto our queue. But 5, 7, 8 are not visited, so we are going to push it onto our. So let us push 5, 7 and 8. So for 5, the weight is 4, and for 7 and 8 as well, the weight is 4. Now since we have operated on 6, so we are going to pop it from our queue and update our visited and answer. So this will be marked it as true, and the weight corresponding to 6 will be equals to 3. The next element is 5, 3, and the adjacent element of node 5 is 4, 6. And as we can see, both 4 and 6 are already visited, because of which we are not going to append anything on our queue. And then we are going to pop this 5, 3 from our queue. After popping 5, 3 from our queue, let us update our visited and answer. So the visited for 5 will be set to true, and answer for 5 will be equals to 3. Now again, the next node is 5, 4. Now let us check the neighbors of 5. So the neighbor of 5 is 4, 6, and since 4, 6 is already visited, so we are not going to push anything on our queue, and we are going to pop this 5, 4. And now we are going to update our visited and answer. So this entry we are going to mark it as true, which was already true. But how about this entry? So this entry, there is some value which is already there, which is 3, and the current value is 4. So this simply indicates that in order to reach 5, there exists 2 paths. One path will give us the weight as 3, and the another path will give us a weight of 4. So what we need to do is we need to choose a minimum between these two weight. So that is why this weight remains as it is, or rather we are choosing the minimum between 3 and 4, and that is what we are updating it over here. So this weight will remain 3. Now the next element is 7, 4, and the vertex which is adjacent to 7 is 6. Since 6 is already visited, because of which we are not going to push 6 onto our queue, and we are going to pop this element. Once we pop this element, these weights will be updated. So this will be marked as true, and corresponding to 7, the weight was 4, so this will come over here. Similarly for 8, so 8 will be marked as true, and 4 will come over here. And in this way, we have formed our answer list, and towards the end, all we have to do is we have to return answer. So that's the discussion of solution, folks. Now let us discuss the pseudocode of this problem. So let us say we want to compute shortest path, and edge list, number of vertex, number of edges, and source vertex is given to us. So the first thing which we are going to do is we are going to form a graph or rather an adjacency list. So let us form the adjacency list. So in order to form the adjacency list, all we have to do is for edge in edges, edge 0 not in graph, then let us initialize that adjacency list. So graph of edge 0 is a list. Similarly, if edge 1 not in graph, then graph of edge 1 is equals to a list. And now let us push the elements onto our adjacency list. So let us do that. So graph edge 0 dot append edge 1. Similarly, graph edge 1 dot append edge 0. So essentially 0 to 1 if there is an edge. So 0 to 1 and 1 to 0 entries should be there in the adjacency list, and this is what we are achieving it using these two statements. And in this way we will be able to form our adjacency list. Now once we have formed our adjacency list, we have to do BFS. So for BFS, let us have our answer, and initially all the values will be -1. Similarly, a visited list, and all the values initially are false, and the size of this list is also equals to the number of vertices. And once we have these two, let us have our queue, a doubly ended queue, and in the queue we are going to store a tuple which is the source and the distance it takes to reach source from source. So initially the distance it will take is 0. From source to source the distance is 0, which is what we are keeping it over here. And this is how we are going to initialize our doubly ended queue. Now we are going to iterate on this queue while queue is not empty. And the first thing which we are going to do is we are going to pop an element from our queue. So source comma weight is equals to queue dot pop left, and let us update our visited and answer list. So let us first update our visited. So since source is now visited, so visited of source is equals to true, and let us update our weight. So if answer of source equals to -1. So this simply indicates that weight of source has not been updated yet, and this is the first time which we are updating it. So all we have to do is we have to just mark answer of source equals to weight. And let us say if answer of source is not equals to -1, then that simply means the weight has already been updated. So now we have to find the minimum weight. So the answer of source will be updated as minimum of answer of source comma weight. So the minimum between these two. And once we have updated our visited and answer node, now we are going to iterate on the neighboring nodes. So let us update on our neighboring node. So for that all we have to do is for target in graph of source, and then we are going to check whether target is already visited. If target is not visited, then in such case let us append target on our queue. So target comma weight. What will be the weight for target? The weight for target will be equals to weight plus 1. And in this way we will be able to find the shortest path, and towards the end we can just return answer. So that's the pseudocode, folks. Now let us see how we have implemented this in Python. So the Python implementation is the same as what we have discussed. Over here we are forming our adjacency list. Once we have formed our adjacency list, we are initializing visited, answer and queue. Then we are iterating on queue while queue is not empty. So this is the logic for BFS. Now the first thing which we are doing is we are popping an element from the queue, source and weight, and then we are updating our answer for source. And then we are iterating on the neighbors of source. If neighbor is not visited, then we are pushing it onto our queue and we are updating our weight accordingly. And then towards the end, we are marking our visited source equals to true and then returning answer. So that's the Python implementation, folks. Now let us submit our solution. So our Python solution got accepted. That is all from this video, folks. In case if you have any question or comment regarding this video, please feel free to use the comment section and I'll try to address them. Thank you.